how to get over those problems. Okay. Um, we are slightly behind schedule, but we can make it up, make up for it. Because the visualization session, I think there are two sessions, one on understanding convolutions and the other one on neural networks and object perception. That's not going to take that much time. So we can shrink that. I mean, we can come up with examples and all that. So in fact, if we get these neural networks sessions right, we can actually, you know, go through the other variants of neural networks pretty quickly. And when I say quickly, I don't mean to rush. The concepts will be easy to understand because these are the basics on which the other more advanced forms of neural networks are going to be based on. Okay, so yeah, so let's start.
Yes.
Okay, okay. So why deep learning? Because we want the network to understand more complex structures, more nonlinear functions, and represent it represented sort of hierarchically. So what do I mean by hierarchical representation? Now, if you look at again, we will now go back to the idea of a human neural network, right? So the way that the shapes are represented in the brain is a motivation for us to develop neural networks. In the sense, if I'm going to look at a car or cow or swan, motorbike, all these categories of items are there. But how does the visual system really learn that, okay, this shape corresponds to this label? Right? Turns out it doesn't, there's no, or maybe there is, there's no like one full pathway which fully represents the car or one neural pathway which fully represents cow. Okay, all these different shapes. What happens within the neural system is, if you look at some of the earliest stages of your brain, like the signal from the eye goes to brain, right? And when I say brain, it's a pretty big structure actually. Uh, no pun intended. It's a pretty big structure, and it goes to one place in the brain, and from there it's connected to the different parts of the brain, right? So it turns out the the place where the visual signal goes to in the brain, if you put a neuron, if you put an electrode, and if you measure some sort of a response, they don't respond to the the shape of a car or cow or bottle or for these fully formed shapes. What they actually respond to are lines. So at the very early stages of visual processing, the brain actually responds to lines which are tilted in different ways, right? Lines with a specific slope, a straight line, an angle line, a vertical line, a horizontal line, right? Lines which are of different orientations. Now, this is very eerily similar to the single neuron within the perceptron idea that we discussed, right? What happens when we want to do complex shapes? We just add more lines and we combine those lines linearly, non-linearly, right? And hence, complex shapes are formed. Turns out your a brain works in a very similar fashion. At very early stages of visual processing, the neurons only can represent lines of various orientation, right? And in further stages of the visual system, the lines are combined to form like a corner, like one line vertical, one line horizontal. Now that's a corner, that's an angle, right? So when two angles are formed, then that becomes some sort of an square. No, that's four angles. So the shapes slowly evolve in the brain and it evolves in a very non-linear fashion, right? As you can see here, at very early stages of the visual system, there are only lines, and then you start getting some curves, and then they start becoming shapes, and finally, somewhere in a very what we call in neuroscience higher levels, at the higher at higher levels of the brain, the shape that you want ultimately forms. Okay, without converting this into a neuroscience class, what we can learn from this. Okay. So if we have to develop complex pattern, we need multiple layers of neurons, right? We need to imagine that this is one hidden layer, this is another hidden layer, and so on. Okay. So at each hidden layer, more and more complex patterns, more and more complex structures are discovered in the data, right? That is called hierarchical learning, where the learning is hierarchical in the sense now, the lines, it's like sounds counterintuitive, but actually efficient system in the sense at the lower layers there are the single lines, right? So you have the nuts and bolts and screws and the wooden boards. Now you can build anything, right? At the second level, these lines are combined to form a slightly complex structure. So now we are hitting the nail on the wood and we are trying to fix a few things. And slowly we combine the nuts and bolts and wood and everything into the shape that we want, right? So at the earlier stages, the representation is simple. It also means that you have the freedom to combine it in any way that you want, right? And that's kind of what we want in our neural representation. So it is actually a very compact representation. It's like how you get your furniture when you order it from IKEA or Amazon, right? Your huge 6 feet shelf comes within like a flat box, right? And it comes with the instructions and it comes with the nuts, bolts, and all the required item. Now it's up to you to build it into a 6 foot shelf or 2 3 feet shelves, right? So that is what is called a compact representation, right? So a k layer network, a network which has a given number of layers, can actually represent a function compactly with a number of hidden units that is polynomial to the number of inputs, right?
Could
So
you say that again? Sorry, I was lost. Can you say that again?
yeah, so I'm just talking about complex representation, compact representation, right? The number of hidden units that you want in the hidden layer, okay, you can represent it as some sort of a polynomial of the number of inputs. So if I have like 21 input layers, I just do like 50 or 60 hidden neurons, right? So the the patterns in the data can be understood better by the hidden layers, right? And the idea for that comes from the visual system, right? So in all the initial layers, it is learning simple patterns, simple lines, um, uh, simple transformations. And as you go within the hidden layer, the transformations become more and more complex and more um, complex patterns evolve within the within the deeper layers of the neural network. Okay, that's the idea behind going deeper in the neural network.
Yes, thank you.
Thank you. Okay, so the idea that we are working with is, okay, we had our ANN, okay, and then we had the problem of back propagation, which we solved. But ANN can only do so much because as the data becomes more and more complex, the number of neurons within a single hidden layer is not able to pick all these patterns perfectly. So what we decided to do, we assumed that the data has a lot of non-linear transformations, which a single layer of hidden neurons, single hidden layer of neurons cannot pick up. So we just added more and more layers. And we assumed that somehow the earlier layers are going to pick up simple patterns and the deeper layers are going to combine these simple patterns to give more complex patterns, which kind of evolved from the earlier input from the previous layers. Okay, this is our intuition. But does it work? It actually works. So adding more layer, actually people get better performance, much better performance. Okay, so the idea that we initially started with, right, that we need to figure out multiple non-linear patterns from the data is finally solved. How did we solve it? We started with a simple neuron, we went on to a perceptron, and then we went on to a multi-layer perceptron, right? And then we decided that, okay, the single one hidden layer is not doing the job. So we added one more layer, we created a fully connected network, an artificial neural network. We introduced back propagation, and still it did not solve a lot of our problems. So we decided that we will just keep adding more and more deeper layers, more and more hidden layers, right? And that actually improved the performance here a lot. Okay, so have we solved the problem of neural networks?
Provided the intermediate layers behave as we expected.
Mhm. Right, so every solution is going to come with a price, right? So of course, adding more hidden layers solves the problem. The network is able to pick up more complex patterns. It is able to perform way better with a lot of where the data is non-linear and all that. But it comes with a price. A deep neural network is going to have a number of problems which we are going to discuss. Okay. And that's what we mean by we mean when we ask is deeper better, right? So of course, deeper neural networks increase the performance, but does it mean that it is by default the way to go, right? We are going to discuss some issues with using which comes with adding more and more layers, right? One of the main issues is this thing called vanishing gradient, right? So when we say vanishing gradient, okay, so when we say vanishing gradient, we you know how the gradient descent works, right? The chain rule. Um, we have our input neuron, we have hidden layer one, hidden layer two, the output, and the error is calculated, right? And how does back propagation work? The rate of change of error with respect to a change in the input weight is what we want to calculate, but there is no direct connection between these two. So we go through the first output layer and then the hidden layer and then the first hidden layer and then the input weight. Okay, that's kind of the idea of my back propagation. Now here, any questions still here? Am I going too fast? I'm going a little bit fast, I know, but it's all good, right?
Yes, Professor.
Okay. Okay, let me quickly go back to the. I'll pick out the chat GPT output that I had for yesterday. Give me 1 minute. Okay, so this is what we were discussing yesterday, right? So if I want to go back to the slide, this is what I have in in that DE by D output, D output by D hidden layer, D hidden layer by hidden layer one times D hidden layer one by D weight one. Okay, that is the chain rule that we are doing. But in the middle, if you see, there is this function, okay, which is basically the output of the neuron, and we have the activation function, right? So remember, there is a derivative term here also. Okay, we need to do a dz by dx, and then do a da1 by dz1. Okay, that's the way in which you are going to implement the chain rule. So in short, we are going to find the derivative of whatever function the z represents. Okay, so if this is a sine or cos, or this is a tan, or x squared, or sigmoid, or whatever, that's we are going to take a derivative of that particular function. That's where it sits here, right? So let me go back to the slide now. Okay, that's what I have in the second stage. So the D output, D hidden 2, D hidden 2 by D1. Within this, within this soup is sitting the D sigmoid Z1 by D Z1 times the weight. Okay, so at some point, we are actually taking the derivative of whatever function is sitting inside the hidden layer. Okay. Now I'll show you the derivative of a sigmoid. This is a sigmoid. This is the derivative of a sigmoid. Okay. So the maximum value that the derivative of a sigmoid can take is actually zero point 0.3. Okay, so any number, if you are going to do a back propagation, let us say that at the hidden layer 1 we are getting a zero point 0.3, and then at hidden layer 2 I am getting another 0.3. It might be much lower actually. So what is 0.3 times 0.3? 0.06, right? And then again, if you have more hidden layers, that's 0.3 times 0.3 times 0.3, right? So that is 0.018, right? So the number, if I take a sigmoid function, if I take a derivative of that, even if it is maximum, like 1, the maximum value that the derivative can take is actually 0.2528 something, but let's round it off to 0.3. Okay. As you go deeper, as the back propagation starts with the last hidden layer and progressively comes towards the input layer, the more the hidden layers, the more the multiplication of a small number. Okay. So by the time the point 3 actually comes to the first input layer, that the number becomes so small, so tiny, that any change in the weight is not going to have any impact in the output. Did you get that?
Could you please come again, Professor?
Okay.
So your audio is in and out, on and off.
Isn't that,
Is my
isn't
audio
that
on and
a good
off?
thing? No, it seems fine to me. Isn't that a good thing though?
Okay. So how was that a good thing? I'll explain the problem once again. Okay. So I'm taking a derivative of a sigmoid here. Okay. So that is point. So here is a point 3. Given that it is actually maximum, it's not point 3. It could be a number way less than this. Okay. And let us say that all the other factors turn out to be 1, and the weight adjustment here is point 0.3. Okay. All that remains is this number point 0.3. And here again I have another point 0.3. Okay. Now remember this chain rule. I'm multiplying this. So point 0.3 times point 0.3. And here again I have a point 0.3. Right? Because dou error by dou hidden 2, and then hidden 2 by hidden 1, and then hidden 1 times the weight input 1, weight 1. Okay. So for coming here, I'm multiplying this number point 0.3 three times. So that is 0.018. So I'm saying that this particular weight needs to be adjusted by 0.018. It's a very, very small number, right? Now, if I'm going to increase the weight by 0.018, and I started with, let us say, 54.39 is the weight that's there currently. What difference would 0.18 make to this number? Right? It just comes to 54.4. That is the new weight that is going into the neural network. Right? So again, the error is calculated, the change in error is calculated, and let us say this time it is some number 0.25. Okay, and then it's 0.2, and then it's 0.2. Okay, now the problem is with this, because of the very nature of the activation function that we are using, the sigmoid activation function, it can the derivative of a sigmoid cannot go beyond a particular number. We have capped it right there, right? So, and we have capped it at a very, very small number. If for every deep layer, if you are going to multiply that number multiple times, the number is only going to get smaller and smaller until no weight, any weight update is not going to have any effect on the output, because we are changing it by such a tiny number, right? This problem is called the problem of vanishing gradient. Did
I'm
you
still
get
trying to
the
figure out
idea
whether it's a
here?
good thing or a bad thing. I'm still trying to figure out
It's
whether that's
a
a good thing or a bad thing.
so it's a bad thing, right? Because I'm making such a small change that the output is not getting affected at all. In my
Right,
first
but then
iteration, it was
but
54.39. My next update is 54, right? So the network is never going to converge.
I understand that. Well, or would it converge even faster? I guess that's the point I'm missing. Because if the error is getting smaller and smaller and smaller, then
Ah,
it's more accurate, faster, and therefore, well, that's great news. I don't need as many cycles. So,
Okay, I'll explain that. Okay. So what happens is, let me quickly get rid of the delta E there. I think that's the confusing thing. This. Okay. And well, I have an output. Let us say for this number 54.39, I'm getting an output of some number 6,000. Okay. The correct answer, this is my y hat. The actual y is, let us say, 49. Okay. So now my error is
Okay.
y hat minus y, whatever number, this huge number that comes here, right? 5,951. Right? Now, in my next iteration, I'm changing the number from 54.39 to 54.00. 54.008. Now, will this change affect the 6,000 number?
No.
No.
No, right? It won't affect much. So, the error is still going to remain a very big number.
Sir, but are you considering an outlier here in this case?
No, it's not an outlier, right? It's how the data, this is how I have started training. This is a random number using which I started training my data set. Because we initially, it all starts with a random number, right? So this is the number I started with. And I want to update my weight based on the back propagation. Yeah, I'll come. I see a number of comments and hands going up. Just give me 1 minute. I'll take it one by one. Okay. The problem is the sigmoid activation. The derivative of a sigmoid is a small number. When I multiply that small number multiple times, the number gets even smaller. So the weight update, which gets back propagated, becomes ultimately so small that no change, I mean, any change is not going to have any effect on the output. Did I answer the two questions, Kalgat and Chandrasekhar?
Digesting it, sir.
It does, except that I guess the whole idea that deepening the layers was supposed to improve the accuracy, but I guess
Exactly.
it's still improving the accuracy over
Exactly.
many epochs, not on the first run.
Oh yeah, I mean it's going to take infinite number of epochs to if it's going to change at this rate, right? So we come to the solution in a minute.
So, but based on what Earl is saying, so here in this case, if we are reaching this point of vanishing gradients, that means we maxed out on this model. Can we say that?
No, we have the network has not started training at all. It is the architecture which is the problem. We decided that we want 5 layers, right? So the derivative of the sigmoid is 0.3. So 0.3 times 5 is now 0.015. That is the amount which the input is getting adjusted, increased or decreased. We haven't even started training the network and we have hit a dead end now.
Got it.
Okay. Yeah, let's start with Suvi. Yes.
Doctor, sir, is this a problem with the network or is this a problem with a layer of the network? Or is it the same
Ah,
thing?
yeah. So it's a combination of two things. The activation function that we are using and the number of deep layers. You see, this problem we did not have in the ANN. In our artificial neural network with one or two hidden layers. Why? Because the number was probably it was still very small, zero point 0.3, but at least the multiplication, the number of times zero point 0.3 got multiplied did not become a huge thing at that point.
Right.
right? Because only one hidden layer, 0.3. So at least there was some change in the weight. It got complicated because of the depth.
Got it.
Okay. So yes, I can see Jeff Bass saying that maybe sigmoid is not a proper function, the activation function. Exactly. So it's a combination of the activation function and the number of hidden layers. I think we want to reach global minimum of loss function, and if the weights become too small, we'll be lost in the middle. Exactly. Yes, correct. We are lost in the middle. We need to find a way to bring it to one to solve it, just thinking mathematics. Exactly. Okay. So we might want to figure out a way to, we might want to use a function whose derivative doesn't shrink the numbers, right? That's what we want to use. And yeah, I agree with both the comments. It's the activation function which is the issue, and the way to solve it is to somehow expand the scope of the somehow expand the numbers in the activation function, the derivative, so that we are not stuck with a small cap for like a ceiling effect is not there, right? That's the way to solve this. Okay. The other problem with this is, I think again this came up in the discussion. We hit saddle points. Okay. We hit steep gain gradients. We hit extremely shallow gradients. So saddle point is basically within your error space. You hit a point like this where you are trying to update the weight, but it is not moving anywhere because let's say you started here. Okay, you started here and you reach all the way here. But you should have actually gone this way, right? So what is the global minima here, right? So that issue is there, and it's complicated by the fact that we are using a sigmoid function, which is kind of a fragile thing, and steep gradient and uh, extremely shadow gradient. Let us say we start here, okay? We start somewhere over here. Okay, we start here, and then we come all the way here, and somehow we have landed in this place. Okay, so on multiple iterations, the network is trying to move in this direction. So the network is trying to move in this direction. Okay, but the weights are not updating because not because it has it has reached a global minimum, but because it has hit a shallow point within the gradient space, right? So for 3, 4, 5 iterations, the weight is not going to change, the accuracy is not going to improve. So we end the training thinking that okay, this is as good as it gets. But if you let it train for a little longer, it will actually reach this point. Right? So all these things are there in the deep neural network, which makes optimization difficult. We have solutions for all this. We will discuss one by one. Okay. I'm just stuck in the first point here, vanishing gradients, where vanishing gradient is basically you're updating the weight, but the a corresponding shift in the output is not happening. Okay, because of a combination of various things. Okay, then the difficulty in optimization. This is again another problem with your deep neural network, because why this was not there in one layer, two layer network? Because the gradient space was not so complicated. Now the gradient space has gotten so complicated because we added 5 neurons in 5 layers. We now have a 25 dimensional space, right? So we don't know what effect changing something is going to have on something else. right? So now the dimensional space is so complicated that it's very difficult to optimize. That problem comes with the deep neural network. Finally, and most notoriously, the overfitting problem. Okay, so we all know what is overfitting, right? I don't have to explain that. Please confirm. Should I explain what is overfitting or we are good there?
Yes, maybe just briefly. Yes, you can. If you can explain overfitting very briefly.
Yeah, just
Okay.
for the concept.
Okay, sure. So overfitting is basically where the whatever model that we're building, and this is not specific to neural network, but this is neural networks are notorious for this. Okay. The overfitting is basically it has memorized the patterns in the data set. So if we are going to if I'm not sure, okay. Can you bear with me for 1 minute? I'll open the first slide, which first session that we had, and I'll explain the overfitting using terms. Okay, let's say this is my data set. Let's say this is my data set. Okay. Now there is a single point here, single blue point here. So you see a single blue point here, right? Let us say that I'm trying to fit a model, right? I'm trying to fit a model. A simple linear regression, no, logistic regression will solve this issue. So I'm trying to draw a line which goes like this. And there is one blue point here, but that's okay. Now this model is going to give me probably an accuracy of 90, let us say 96%. Okay. Now, if I get too ambitious and if I try to account for every data point within this scatter plot, I would ideally go for a shape that looks something like this. Right? Do you agree? I would go for, instead of a simple line, I would draw a shape.
But that would be overfitting, right, Professor?
Exactly. That is the point of. So I start here and go here, and then now this perfectly explains the data. I'll probably get 100% in my training data accuracy. Okay, but if I had had another line, if I had my original line, which was like this, okay, a few red points here, okay, would have been classified correctly, right? The blue is actually an outlier, probably, right? Now, for the sake of fitting this one blue data point, I did some non-linear transformation. I created, instead of a line, I made it into this very weird shape. And how did I get this weird shape? By combining different linear lines into some sort of a non-linear equation. That's how I got this very complicated red line, right? But a single line would have been enough. So what did I lose? What did I gain? I perfectly explained the training data. But you see the black the X that in the red part of this of the plot, those red dots, those black X's should be classified as red dots, right? When the new data comes. But that is now falsely classified as blue. So I'll get a training accuracy of 100%, but a test accuracy or when I actually deploy it in real world, my accuracy will drop to 85, 84 percentage, right? That is overfitting. Okay, I overfit. I explain my training data perfectly at the cost of the neural network not learning the general aspects, but being very specific to the data set that I have provided. And neural networks are notorious for this. Okay, so what should have been done? No, in the problem statement that you see on the screen, what should have been accomplished using a single neuron? So overfitting occurs when we are accounting for outliers. That's one of the situations. Overfitting occurs when the model perfectly explains the training data. It has memorized the training data rather than learned from it. So the knowledge is not transferable. It's unable to transfer the knowledge that it gained in the training data to an unseen data point. That is overfitting. And one of the ways it can happen is taking an outlier very seriously. That's not the only way in which things can go wrong. Right? You see now what happened with the problem on the screen? What could have been accomplished with a single neuron, which is a single line? We unnecessarily brought in a neural network. We had more, we had one hidden layer with 3 neurons and then added one more hidden layer with 2 neurons. So now it perfectly created the shape that we wanted, right? So the training accuracy was great, but the test accuracy went down. Why? Because the shape of this line doesn't truly represent the data. It memorizes the data. Okay, that is overfitting, and neural networks are notorious for this. Okay, so typically that's what's going to happen. The training accuracy is, we don't want 100% training accuracy. If there's 100% training accuracy, then in all likelihood, there is some sort of an overfitting happening. Okay, so 97.36 is my training accuracy. My test accuracy is around 90, which I can live with. But if my training accuracy is 100% and my test accuracy is 86, then there's a 14% difference, and I'm not okay with that kind of a difference. For neural network, is that for called hallucination. See how easy it is to connect a neural network concept to an LLM concept, right? It's, you can say it both have common origins in the sense that it is not able to represent a new data point. It is not able to predict for a new data point. It is relying too much on the training data. But I can't really say that hallucination is the LLM version of data overfitting. But the origin is the same, the concept is the same. Yes.
Professor, hallucination.
Okay. So yeah.
Hallucination is about generating which do not fit to the truth, right? And here it is basically learning noise, right? And learning noise cannot be a hallucination, right? It can be analogy, it can be equivalent, but it cannot be that, right?
Correct. It's not. That's why I said it's not. It
Okay.
could be a similar concept where there's a mismatch between the training data and the unable to represent a new data. Unable to truly represent a new data where there is a fundamental mismatch.
Okay. And another thing, Professor, now when we pass through multiple strands of data, like multiple records of data, and if a particular neuron's weight, if it keeps toggling, it goes up and down, right? And which that it is not getting harmonized. And in that sense, that weight update has to be discarded, right? For essentially, this is what we are doing in mini batch because we are not considering one strand of data. We are taking a bunch of data and then getting into that. But ideally, in this back propagation also, like like let me say that if my entire neural network's task is to detect a spectacle, and it might see that there is a glass, there is a frame, there is a ear holder, and so on, and these three pieces, and there could be three different sections of network. Now, for detecting the spectacle, these three parts would contribute, and how much weightage would it do? Like instead of 100%, it will become 30, 30, 30, and naturally that is how we are seeing the vanishing gradient because the values are becoming smaller. But the thing is, like different spectacle.
Wait, I didn't get the idea of the 30-30. What was that?
Okay, if three different features, right? If I'm taking a cat, to identify a cat, the eyes, nose, and ears, they contribute to recognize the cat, right? In that case, the split weightage of each of the feature is 33 percentage, right? So
Okay.
now further, when I'm looking at the ear, like whether it's a pointed ear or something, it will get further divided into subgroups, and that way, like as we go deeper backwards in the network, the contribution of the feature will get divided, and it will become zero point 0.3, 0.03, and so on, right? Now, this is the way the vanishing gradient naturally happens. Now, my question is, but if we look at multiple different years and all those years, like when we add together, all of them will fall onto the same year type. Now, the incremental weightage should be higher, and this can be sensed through the weight directional harmonization, right?
So I have some issues with your first understanding of the of how the feature representation happens. Okay. So when it so what you said, it need not be necessarily the truth in terms of how you connected the features and the vanishing gradient.
Mm.
So vanishing gradient is basically it could have it is at a point where it has not even learned the features. It has not even come to the point where there is a pointy ear or nose and all this.
Mm.
Okay, because of the sheer depth of the neural network, it started with a random weight and it is still stuck there. We haven't even started training and we have hit a roadblock. That is vanishing gradient. It can happen somewhere when you are trying to
Fine tune,
when you are in the middle of the neural network training.
fine tuning.
In which case, it is an not fine tuning. I wouldn't say in the middle of the neural network training, if it happens, it becomes an optimization issue rather than a vanishing gradient issue.
Got it. Got it.
Right? The saddle point and the shallow network and all that. Right? Vanishing gradient is basically it hasn't even started anything. The process has not even started.
Got it. Got it.
Okay.
Yes, boss.
Great. Thanks. All right. So, how can we address these issues? Okay, we have multiple solutions for all of our problems. Firstly, you see, the problem with the vanishing gradient was the activation function, right? Um, we can use a different activation function. Instead of starting with random weights, we can systematically come up with something, and we can initialize with instead of random numbers, we can come up with some set of numbers which is likely to win. Okay, we can reprocess the data somehow. We can make some adjustments with the gradient descent algorithm itself. Okay, these are the four categories of approaches that we are going to look at in order to improve the training process. Okay, so the first is the problem of vanishing gradient. You see, the problem with vanishing gradient was the derivative of the sigmoid. Okay, so what we would do is replace the sigmoid with something where the derivative most likely matches the input. Okay, so the activation that we are going to, the activation function that we are going to use is something called a rectified linear unit. Instead of sigmoid, we are going to use a ReLU activation function, or in this called ReLU, where we are going, the x and y. On x we have the x, and on y we have the derivative of x. So as you can see here, this is a largely linear function, but it caps all the negative values. Okay, so any negative number, because we don't want negative numbers, because we are assuming that the gradient descent will actually pick up the direction in which we are going to update the weight. So plus or minus, the actual number is going to be determined by the gradient descent. So we are not too much worried about the negative side. So anything less than zero is capped to zero, which means that those weights will never get updated, right? And on the positive side, it's going to be linear. So for every derivative, for every number, the derivative of the number is going to be the same number. So now this is actually a very, very good thing, because all of our issues with the sigmoid that we faced, where multiple multiplications resulted in the number getting smaller and smaller, that doesn't exist now. Okay, so if the number is 0.5, it remains 0.5. Okay. If the number is 0.9, it remains 0.9. And so the computations become more plausible, and hence weight update is much more efficient. So the first step we are going to do is replace our sigmoid with the ReLU activation. And then we are going to have some modifications of ReLU called the leaky ReLU, where instead of completely reducing the negative values to zero, the numbers are going to, you know, we will progress slowly on the negative side, but linearly on the positive side. Okay, that is leaky ReLU. People mostly they don't use leaky ReLU. It's ReLU or sigmoid. Sigmoid, if we want, if our network is small, if we go deeper, we use ReLU. That is almost like a standard. Okay.
Professor, ReLU
Yeah.
will have the same discontinuity issues, right? In while differentiating.
What discontinuity issues?
When if you look at the negative side of it, it
Ah.
will still be, it will not have any variation. So when we are approaching towards the positive side, we won't get any guidance, right?
Like here, you mean this side?
Yeah, in the side. Like so, let's say that.
Correct.
Like this is the reason. Like I mean, due to two reasons, we were avoiding the step function. and one is the discontinuity, and the other one is like guidance towards the optimization. So that way, when compared to the leaky relu will have the same problem of avoiding guidance, right?
Yeah, yeah. But on the positive side, on the x where the x is positive,
Yeah.
it increases linearly.
Hmm. Hmm. So this function will be good as long as it is immaterial to us, whatever may be the negative value.
Yes, and that's why, as I said, where the delta E and the amount of change
Hmm.
is going to be a function of the gradient descent algorithm itself.
Hmm. Hmm. Hmm.
So as long as that's taking care of the direction, we are going to preserve just the number, the magnitude.
Good.
Okay. Yeah, go ahead.
Yeah. Sorry, I think I missed the part on the how is it like can you show in numbers and in function how it's not decreasing the number again? The other one is 0.3 and then times 0.3 and then it's decreasing. But now it's the same. How does it work? Sorry.
Okay. So the problem with my sigmoid was not the 0.3, but where the 0.3 is coming. It's not even 0.3, it's around 0.25 something again. So the problem with my sigmoid is even if the x value is as high as 1, the derivative of x is capped at 0.25. Right? It's a relationship between this and this, which is the issue here. So what we have instead in our ReLU is if the input is 1, the number 1 is preserved. It doesn't get capped to 0.3 because the derivative of 1 in my ReLU was actually 1 only.
Mm-hmm.
Right? So
Because
whatever
of the
number
function.
0.9, 0.95, 0.8, yeah, because of the activation function that we are using.
Yeah. Okay, got it. Thank you.
Yeah. Okay, so the first is a better activation function. That's actually the easiest, most efficient. The things that we are going to talk about in today's session are mostly like prescriptions. I'm going to say this is what we are going to use in neural network. I was just setting the context in the previous two sessions. Okay, I was just telling the problems as to why we came up with these prescriptions because it's almost standard to use tanh or sigmoid or relu. But there are whole other hundreds of activation functions. Why we don't use them is because of these problems. So I told the problem first, and then I came up with a solution, and then I'm going to give the prescription for whatever we are going to discuss today. Okay, let us say the next approach is improving the gradient descent, right? So gradient descent people don't use anyway nowadays. They use only a modified version of gradient descent, which we are going to look at now, right? But the core is the gradient descent, right? So similarly, weight initialization, for all these things, whatever we discussed till now is only the historical idea of how these things evolved. The variations will be discussed in the session and they will be given as prescriptions. Like when you build a neural network, use these. Use this initialization, use this gradient descent, use this activation function, use this regularization. I'm going to give some prescriptions like that. Okay. Okay. So the gradient descent, how we saw the problem with the gradient descent algorithm itself. Okay. We also saw how the learning rate can have an effect on its ability to converge, the gradient descent's ability to converge, right? So if you use a very slow learning rate, it becomes too slow for the network to converge. if we use a very fast learning rate, it will kind of bounce off. So what I mean by bounce off is, I think that's the next slide. Yeah. So it kind of bounces off like this. And small learning rate will lead to slow convergence. Okay. So what is the solution? We're going to come up with a method where the learning rate is dependent on the slope of the magnitude of the steepness of the curve. Okay. So we sit and monitor the loss function as the neural network is training. We start with some learning rate. Okay. And again, this is very similar to what we discussed yesterday. A good learning rate should converge the network slowly but steadily. A low learning rate will take a lot of time to converge. A high learning rate will keep bouncing off, right? Like this. So it's never going to reach the minimum. So it will kind of flatten too soon. So one of the things that we can use is what's called a learning rate decay. So we start with some small number of the learning rate, and then we try to, or we start with a big number, with a big number of the for the learning rate, and then we come to a point where um, where the network is not learning anymore, right? And we suddenly change the learning rate now. Okay, we modify the learning rate such that the network starts training again. So we start with a big number and then progressively reduce it to a smaller number. Now, if we had started with the small number, in order to reach this point, it would have taken a very long time. A very long time, right? If we did not modify the learning rate, it would have saturated here, like this. Now, the learning rate decay kind of addresses both, right? So it keeps monitoring my loss function, loss, and the error and all that. It keeps monitoring my loss function. And if it feels that the network is not learning, it suddenly modifies the learning rate. Let's say we started with the learning rate of 0.9. Okay. Now, if the network doesn't converge, it just changes it to 0.75. And that goes on for some time. The network trains, and again it hits a plateau, and now you change it to 0.5. And then 0.1, and somehow reach the attain convergence. Now, if you had started with 0.9, it would have taken a long time to converge. Okay, so the first problem we are going to address is the learning rate issue. The learning rate issue can be addressed by using this concept called decay, learning rate decay. Any questions still here?
So I just want to clarify. So the loss function means how bad is your model? It's calculate the errors of the model, right?
Yes.
And the
Yes.
higher it
Correct.
is, then the worse the model is. And so it's supposed to
Yes.
be decrease. Okay.
Correct.
But now we're talking about how it should decrease. And
Yes.
and if it decrease, then it's good. But like for the first one, the red one, it goes in straight line. Why is it worse than this decade again? Oh, because the slope is not that steep. So we want to make it
Yeah.
reduce and to
Yes.
reduce the
It's going to
time.
take a long time. It's going to take a long time to come to the same point. You see, in how many epochs I arrived at this point? It took much more epochs to come to the same point. Yes. Yes, Niyas, yes.
And between this the right one, the black right one, and the right black one, and the red on the left, which one is better in model again? This
So
is a good learning rate.
yes, so the red line here and the black line here are pretty much the same thing, except
The same.
this is happening in steps and this is happening. This is the ideal scenario we want, right? But it's very difficult to get get the correct learning rate, which will give me this shape.
So on the
Right?
left is the ideal one. In the reality, it's the right one, the black one.
Yes. Very likely this is what will give us quick convergence.
Got it. And so I think I like at the like the edge of going down. Does it mean that like we do something or something like major findings in the function? I mean, in the training, like the improvement in the training that make it's gonna go the error rates go down a lot. That's what we want, right? Yeah.
Yes. We want the error to come down quickly, but also steadily.
Got it. Thank you. Thank you.
So
Thank you.
here the
Yes.
last function, it can be accuracy or precision or recall or MAE, whichever we choose relevant for our model, right?
So, quick correction here. Accuracy, error for all metrics, loss function is the function. So, that's the MSC or SSC or whatever. If it's accuracy, it's going to be in percentage. What I want to monitor, if I want to monitor the accuracy, we'll have a reverse plot which goes like this. I mean, we can monitor anything. Here we are monitoring the error. And so I'm taking a metric for the error, which is the loss function.
Okay, it has to be a mathematically coded function. I mean, it has to be in the f of few variables, that form it has to be.
Yeah, so if it's error, it has to have an error term. Like x minus x by y minus y bar, the whole square sigma. Right? That is SS. If I take, it's like simple percentage. That's the metric I am monitoring. But so neural networks, they don't understand accuracy. They understand only the error term. So internally, even if you are monitoring the accuracy, it is the loss function which actually determines the training. So what I'm trying to mean, you started with accuracy, error, loss function in one bucket. I'm just like making this subtle difference of metric is different, the function is different. That's it.
Understood. And
yeah, go.
I can choose only one loss function. If I have two different objectives, I should find a way to bring them together in one equation so that it can be optimized. For example,
as in, I didn't get that. Yeah.
In case of regularization, I have two objectives. I want the weights to be smaller, but at the same time, MSC to be less. So
why do you want the weights to be smaller? Why are you concerned about that?
See, but I am talking about the ridge inequality, right? Where I don't want a bloating of the weights, which goes into false learning. So, in the L1 and L2 regularization types, right? In that case, I have naturally two objectives. One of the objective is that my loss has to be minimized, and the other one is the weight have to be as possible for the corresponding loss objective. So in such case,
so here the problem we're talking about is related to the exploding gradients, the opposite of vanishing gradients, where the weights get exponentially higher, right? there are ways to control that.
Okay.
Okay. So if you are doing two things, one is a regularization, one is an
Hmm.
optimization.
Hmm.
So we are going to take two approaches to solve these two problems.
Got it. Yeah.
We'll talk about exploding gradients
Sure.
sometimes.
Sure.
Sometime when we do images, we'll
Hmm.
do exploding gradients.
Thanks, Professor.
Okay. Okay, I'll try to explain the abbreviations which people are trying to use when they talk. But feel
Sorry.
free to just
Yeah.
interject and ask. Yeah.
Yeah. Sorry. Actually,
Which
sometime
which
before,
part of the discussion do you need?
yeah, sometime before Nias was asking something. I honestly didn't understand because we are understood very clearly in the picture. Uh, and also, we got to understand the green, the red, and everything. No, but the last discussion when Nias was asking, completely I lost. I did not even got uh, what we
Never
were
mind.
discussing. So I little got fear. This is I noticed many times. So what is important? First of all, we are not all of them from the mathematical background. Okay, so it's yeah. If we are using something out of the slide, it would be very nice. We can also explain with the simple terms. Then you can easily connect. Because now I little lost and I not
No
all.
problem. No problem.
That's
I get the concern. I'll probably give a disclaimer that this is we are going a little bit one or two sessions ahead. Okay. So whatever Niaz asked is going to come somewhere in the future. So he flagged a concern that okay, I'm multiplying numbers. If I'm multiplying small numbers, then those numbers become even smaller. But if I multiply big numbers, those numbers even become bigger, right, in back propagation. Do you understand the concept, right?
yes, that
So
is true.
he said that should we really be concerned about keeping the weights at like a minimum number? And all I said was the concern is real, but we'll address the solution later. That's all.
Sure, sir. We will learn it later more detail. This is very clear. So when we are using those complex words,
Sure. Yeah.
that's what we cannot get. If it's simple analogy, then we can easily understand. So, for example, the gradient and everything is like simple explanation, and it is very good in the presentation. But suddenly we are using some complex
Yeah.
stuff. It is
I mean
difficult.
that. Yeah, I get it. I get the concept. Okay. All right. So the learning rate decay is the first thing that we are going to implement. Did any other hand go up? Did I miss something here? Okay. Good. Now the next thing is I'll talk about the problem first. In gradient descent, for a given learning rate, what's going to happen is the steepness of my I've now this u is a very linear u. Let's take another gradient space where the shape looks something like this. Now what's going to happen is there's going to be a learning rate here is going to start with the error which it found here, and then I'm going to have a learning rate, and or I'm going to get rid of this. I'm going to draw a slightly different figure. Okay, I'm going to draw an error space that looks something like this. Now, if you look at this, the the steepness of this part of the curve is different from the steepness in this part of the curve, right? Now, what's going to happen for the same learning rate in this part versus in this part? if I use the same learning rate, it's going to progress at a different speed here, right? But for the same learning rate which worked in the past, it's going to give a different error and a different weight adjustment for this part of the curve. The curve is basically the error space, the W naught, W1 error space. I'm taking only two variables. Imagine this as this multi-dimensional complex error space.
Is this
Okay?
loss and epoch? Loss and epoch
Yes.
on X on Y X. Okay, thank you.
No, so it's between epochs. So in the first epoch, it is updating the weight. The learning rate is remaining the same. Okay, the learning rate alpha is remaining the same. Okay, one epoch it works because the error is getting updated. The weight is updated in this part of the curve, right? So this is one epoch, and then the second epoch, third epoch, fourth, and we keep coming here. Once we reach this point, the steepness of this part of the curve is different from the steepness in this part of the curve. So for the same 0.01 learning rate, I'm going to get a different progression, right? I'm probably going to need many more iterations within this small part. Remember, nothing changed except that that is the nature of the error space, of the feature space. That was part of the gradient of the vanishing of the, what do you call that? The saddle problem or the, okay, or the steep gradients problem. We started with this point. We had fixed a learning rate. Things are working very nicely, right? Until it got here. Right, so one way to address this is to have a decay value where I'm just going to quickly increase that, change the learning rate so that it goes slowly. But remember that won't work in this case because if the learning rate is going to decrease, it's only going to make things worse, right? So what we need here in such situation where the error space is uneven is some sort of a memory where what we are going to call momentum. Okay, so it should travel in the same speed. The change in error should travel in the same speed as it traveled in this part of the slope. Okay, so it should sort of gain momentum here, and in the same momentum, it should travel in the same speed in this segment of the curve as well, in spite of the difference in its steepness. Okay, in terms of regular life, we are going to think that I'm coming down the slope in a bicycle, right? And I'm going to let the speed that I learned here affect the speed in which I'm going to travel in this part of the slope. That's the bicycle analogy of how how we want the weight to be updated. But mathematically it doesn't work like that, right? So mathematically, what we're going to do is we're going to remember we're going to remember some of the parameters that we were working here, and we are going to like keep log of all the previous weight updates, if not all, at least a few previous updates, so that I will remember how in what speed I traveled in the past, and I want the same speed to be replicated in this not so steep part of the error space. Okay, so we want some sort of an error term of a momentum term which can keep log of the previous weight updates, the magnitude of the weight updates which happened in previous few iterations. I'm going to quickly go through the chat box. The rich or regularization was taught by Dr. Larson in fundamentals of machine learning. Okay.
This is to address the concern because one of the student was feeling
Sure,
that
sure, sure.
it is beyond the course, right?
Sure, sure. Thank you. Okay, so that's what we want in terms of how we are going to update the weight, right? So if this is my gradient space in this very weird kind of an oval, uneven space, okay, it's going to travel. I mean, for a single for set of single fixed parameters like learning rate and all that, it's going to travel. There's going to be a jump in one direction, whereas there's going to be a smaller jump in another direction, right? And if this keeps on happening, convergence will take a very long time, right? That's the premise on which we are operating. Okay, it's going to take a long time because the feature space is so uneven that the learning rate which worked in one direction is not working in another direction, right? So what we want is some sort of a memory where it can remember the previous few updates, and then now the weight update is going to happen in relation to the previous updates that happened. Okay, so instead of taking the latest gradient, we give more importance. We take the average of the past few gradients. Okay, so this ensures that there is no like from one point it goes to another point, and then it goes to another point, and then it goes to another point, and that goes on, and it is just going all over the place within that feature dimension. What happens with averaging? This direction, and then this direction, and then this direction, kind of averages out as this single direction, right? So when the next update is happening, it is happening with respect to the previous updates that happened, rather than treating this update as like a fresh thing. That we are going to call momentum. Momentum is basically a term. I mean, it looks like physics, but it's basically some sort of a moving average of the previous few weight updates. Okay. Did you get the idea of momentum?
This is essentially the thing that what I was talking about in the previous thing. Like a neuron's weight, if it keeps going wavering on the positive and negative, like will we be able to, take a average or cumulative call? So yeah, and now I could relate.
Yeah. Okay. So I'll continue with momentum. I think it's time for a break now. Let's take a 10-minute break and come back. Uh, and I think we can continue from where we left off. Okay. Okay, and we are back. Yeah, exactly. So Simon is asking if nowadays the training is a combination of multiple methods like dynamic learning rate and momentum and all that. Yes, exactly. So as I said, I'm just setting the context, but I'm going to give a lot of prescriptions like no, use this. Like how for activation function, I just simply said if you go for a deeper neural network, go with really that's all, right? So, but no, I should use radio is what we were trying to understand till now. Okay, like that. I'll give multiple prescriptions, like, do this, like that. Um, but we need to understand, get the background of why we are doing something, right? And how did it evolve into what it is currently. And that's what we are trying to understand. So I hope you can see the slides, the full screen version of it. So basically, we want to include the momentum term to the gradient descent, where we are going to deal with the multi-dimensional space problem, right? The core of the problem being a learning rate which worked for a particular steepness is not going to work for another steepness, right? So here, for okay, so for this segment, um, the same learning rate gave um, converged quicker, like within three iterations. Within three iterations, we covered the distance, but for the same distance in a different slope space, different steepness of the slope, we are going to take 5 or 6 iterations, right? This might seem like a simple thing, but it's in reality, it can actually cause a lot of confusion, and we'll be wondering why the weights are not getting updated while it got updated in the past, right? So, so one way to address that is we want to have a moving average of the previous weight updates. What the moving average does, it smooths out the roughness of the gradient space, right? So if I went like this, like this, like this within the gradient space, the averaging is going to convert it into a nice, regular slope. So moving average is one thing. I mean, there are variations of this where I can give more importance to the most recent weights and discard all the previous weights which were there 10 iterations ago, 20 iterations ago. Again, that is a hyperparameter which I can choose, and I'll tell while training, okay, ignore the weight updates which happened 10 iterations ago. Why? Because I was in a different part of the slope space before 10 iterations. Now I'm in a different part and take only the weight update and the learning rate that you used in the last 5 or 6 iterations, right? So I mean there are some variations of this, um, but the idea is the momentum term. So it's almost a standard to use stochastic gradient descent along with the momentum term of whatever value. we keep it at 0.9. Okay. Now, if you see here, this gives a nice visual of how quickly each of these algorithms is going to attain my global minimum. Okay, we see that it's the RMS prop, which is the best algorithm. So RMS prop is basically, again, it is an optimizer where where there is another problem here going on. If you notice closely, a learning rate which might work for one weight might actually not work for another weight. Because in back propagation, the error is distributed across different neurons in my hidden space. Okay, so a point 0.1 learning rate might result in an update of 0.5 or 0.6 in weight number W5, but in weight number W10, it can actually change the weight to 10,000. Right? So a single learning rate might not work for different iterations. It might not also work for different weights within the neural network because of the sheer numbers which are there. Again, this is a problem with deep neural networks because now we have like 5 layers, each with 6 or 7 neurons. So 5 times 6 is around 30 neurons we are having. So we have W30 terms. So a weight update that works for W29 might not actually work for W2. So what can we do? That's where RMS prop comes in the picture, which is root mean square propagation, where the weight update is weight specific, is neuron specific. Okay, so we introduce a term, it's not magic really. If you go into the real math of it, it is just like a two-step function where it just says that if the number goes beyond something, then cut off the rough edges, and if the number goes less than some, if it's too low, do something. If it's too high, do something. So it's pretty much it's a very fancy thing. Um, but that's what happens in the back end. Okay. But the way that we are going to understand it is the weight update is going to be neuron specific. If a neuron requires a bigger weight update, the weight update is going to be higher. If a neuron requires smaller weight update, it's going to be smaller. That is RMS prop. Okay. Root mean square propagation, and that's why that works best. Because now the weight update is not related to the gradient space alone. It factors in the fact that different neurons might require different weight updates. Okay, so that is RMS prop, and then the first one was our momentum. So gradient descent with momentum. Finally, there is something called adaptive moment update, which is going to be ADAM. Adam basically combines both of this. Now, if you look at the two-sided nature of the problem, on the one hand, we are working with the bumps in the gradient space, right? Simultaneously, we are also trying to customize the weight update at the neuron level, right? So, while RMS prop works at the neural level, the momentum gradient descent with momentum navigates the weight update, taking into consideration the nature of the error space, of the feature space. Adam basically combines both. So it takes one momentum, which is the momentum that comes with the gradient descent, and there is a second momentum value which we give, which is basically the RMS prop update. That number will basically decide at what point we want to consider a number big enough to clip it or small enough to just retain it. Okay, so basically the Adam update is going to do the weight update, taking into consideration the roughness of the feature space and also the fact that different neurons might require different weight updates. Okay, so it takes in both these factors, and that's what works in most cases. So another prescription that I'm giving is use Adam optimizer. Okay, so I'm going to give Adam optimizer. Optimizer is Adam, learning rate is some value. I can also give like a big value for Adam update where I can define what is beta 1, beta 2. We'll probably look at it during our lab session. Okay, so the second prescription basically is use Adam update because that is very efficient in most cases, or use RMS prop, which is also equally efficient. Okay, so the first problem of vanishing gradient, we addressed it by changing the activation function from sigmoid to ReLU. The second problem of the optimization of the unevenness of the error space, that we are addressing using Adam optimizer. Now this also takes care of multiple issues which we saw: the saddle point gradient, the steep gradient, flat gradient, plateau gradient. So a lot of problems the Adam is going to solve. Any questions still here? Okay. The next is what is called weight initialization. Remember, we tried to initialize the weights by using random numbers, right? When we started with the neural network, all the initial weights we assigned random numbers, and that's how we started training our neural network. Now, without giving too much context, the and then people started using, instead of some big random numbers, people started using numbers from the z-scores, basically from a normal distribution. From a normal distribution, take numbers which are like 2 or 3 standard deviation and all that. And that also gave some problem, and slowly things evolved until now. The almost again standard is what's called Xavier Glorot initialization, where where the numbers that we assign to the initial values is not random, but it is a function of the number of layers. Ni is the number of layers. Okay. Layers or neurons? Not sure. So, to the values chosen from a random uniform distribution that is bound between the significant value, where n is the number of layers within that neural network. Okay, and again, we don't have to do any of this. We just set it to, when we define it, we just say kernel initializer. We set it to Glorot normal. Okay, so that takes care of some of the initialization problem. Because the thing with random numbers is it can go from minus infinity to plus infinity, right? So minus 50,000 is one random number, and then another 10 crores is another random number. 0.5 is also another random number. So if you have to update weights within this huge range of values, then again that becomes a little bit inefficient, right? So we start with some manageable numbers. Okay, and that's why we come up with the kernel initializer hyperparameter, and mostly we set it to Glorot initialization. That is one of the ways in which we can improve the neural network. We'll come to autoencoders and how it is related to initialization, but we will quickly move on to the final problem which we mentioned, which is regularization. Okay. Just give me 1 minute. Yeah, Jansi Rani, go ahead.
Professor, in the earlier slide, we saw this initialization. Is it so? It is always we use this only one method, or do we have also multiple method for this?
So again, we can just use a normal distribution. Okay. If it's normal distribution, the numbers are going to just change, and we can also give the standard deviation. So minus 1.96 to plus 1.96, just some narrow range of values,
In the
and
early,
that is just the starting point. As the network trains, those numbers will become either big or it will become small.
okay.
Okay, so we can use some standard normal distribution, some probability normal distribution, or we can use Glorot normal distribution. This works best in most of the deep neural network problems.
Yeah, got it, Professor. Thank you.
Okay, finally, we are going to address the third issue, which is the problem of overfitting. So we saw that neural networks are notorious for overfitting because as we add more and more nonlinearity, we can build all these very complex shapes, but ultimately the true representation of the data might be lost. So the process of addressing the overfitting issue is what's called regularization. Okay, so regularization is a way in which we are going to address the overfitting problem. One of the most proven methods to addressing the overfitting problem is using this concept called dropout. So dropout is basically again very biologically inspired, and it was part of my postdoc also. Um, so basically, what we want to address here is I'll tell a little bit about my postdoc work because it's very easy to understand once we understand the neural aspect of it. People by some unfortunate turn of events are born without vision, right? Um, but once they regain the vision after few years of being visually impaired, like completely almost zero vision, what happens is the vision doesn't really develop very quickly. Okay, it takes some time to develop. And if we go back to the brain and try and understand what's happening, usually we go back to the first lecture where we talked about the 100 billion connections within the brain, right? So when we are born with probably trillions of connections. What happens during learning is some of the connections get strengthened, some of the connections get weakened. The ones that get weakened just kind of die off. The ones that get strengthened, they they become stronger and stronger. And the example that I used in the first class was, let's say a neuron is designed to get input from the eyes, visual neurons. Okay. Now, what happens to these neurons if they do not get input from the visual system? Like as in the case of my postdoc work, people who are born without vision, with visual impairment, right? What happens to them? What happens to those neurons which are designed to process visual information? So research has shown that these neurons actually they can adapt and they can reallocate some of their resources to other senses like auditory or touch or other olfactory. These neurons they can be since they are waiting for visual input, they are not getting visual input. So the system doesn't want to waste this resource. So it reallocates this neuron to some other function. It will not be as efficient, but it will still do a kind of some sort of a job. Now, what happens to this neuron if it starts getting visual signal? Like in like people, let's say they undergo some sort of a surgery and the ability to see comes back, right? This neuron is born to do the visual function. But since it did not get vision input, it got reallocated to, let us say, auditory. Now vision starts coming again. What will this neuron do? How will it respond? roughly, it kind of does both the functions, but kind of inefficiently. Okay, it does a little bit of auditory, it does a little bit of vision, so people can see, but this resource is used for two purposes now. It's used for vision and it is also used for auditory, right? So people took inspiration from stuff like this and they decided, okay, the problem with overfitting is basically this neuron is learning too much, right? This neuron, which is, let us say, doing a PCA, is doing only PCA, right? It's not doing x squared or it's not doing root x or it's not doing anything else. It's only doing PCA, right? So that kind of overfits for the problem. So people said, what if we reallocate some of the neuron to perform multiple jobs, right? And that's the concept of dropout. So what happens during neural network training is when in one iteration, this particular neuron is active, okay? So it learns something. It learns some transformation. It learns some combination of information. It learns some pattern. Now, in the next iteration, this neuron is turned off, right? So the input from the previous neuron, it comes here, but it doesn't really do anything to that and kind of passes it directly to the next layer. So now whatever job this neuron was doing has to be performed by the neuron in the next layer. The story doesn't end here because only if what this neuron did was useful will that operation be repeated. If whatever this neuron did was not useful, the next neuron will do some other thing, which will still represent the data probably more efficiently, right? So instead of training this neuron to do just one job, we are training the neuron in the next layer to kind of double check if this did it correctly. Now, what's happening at this level in the third hidden layers neuron? It was already doing some job. On top of that, it learns to do the PCA also. Why? Because that's the data that it got in this iteration, right? So this neuron is not doing two jobs. This neuron is now doing the same job, but it is sitting silently. It is not getting involved in a few iterations at all, right? So now the data doesn't overfit because each neuron is not doing just one thing. It is capable of true learning. It is capable of being adaptive in the things that it learns. Okay, so in that sense, the problem of overfitting doesn't happen. Is the concept of overfitting clear? Yeah, so clear, yes.
So I think example very well explained in context to biological neurons. I didn't really understand how it relates to compensating for the overfitting challenge. If you can repeat that again, please.
Okay, so in overfitting, we are assuming that it is just memorizing stuff. Okay, so when I say memorizing, this neuron which is sitting here, some data comes. During the first few iterations, it is learning that, let's say, doing an x squared transformation helps me represent the data better. So it just does the x squared. It's trained to do only that. Okay, so gets comes in, it does an x squared, it sends it to the next neuron. The next neuron gets the x squared value and it does something on top of it. Okay, now this is almost like memorizing the process. It is like a workflow automation. Irrespective of the input, beyond a point, it is only doing a memorization. Now, what dropout does it? I am turning this neuron off, okay, and I am sending this input directly to the neuron in the next hidden layer. Now, this neuron was used to getting x squared values. Now it is getting a different set of values in this iteration, right? So whatever it did with x squared, this time it is not working because the incoming values are x. So now this neuron will figure out that probably x squared is not good. I should do x cubed, which this neuron should have figured out. It did not because it overfit.
And that's in a DNN that is done intentionally versus in a biological network, it's done unintentionally.
Yeah, correct. So in a
Got
biological
it.
thing, it is a result of a situation. Whereas we take inspiration from that and we implement dropout and we say, let a neuron do more than one job.
Got it. Thank you.
Okay. That way it doesn't memorize the data, it really learns from the data. Yeah.
Sorry, I do understand. But it's I think I missed just like 10% of it. Like when the job is sent to like the A person doesn't do it, then the job is sent to the B person. And then the B person figure it out that, oh, this is not good. And then but so the A person is just called drop out. But like
Ah,
so sorry,
okay.
but how
That's
is everything related? Yeah.
correct, correct. So that is the concept. Okay, that's the concept. But how we are implementing it is in one iteration, I'm turning off a few neurons, like how I see this X, right? So instead of being fully connected, not every neuron gets input from every other neuron in the previous layer. Okay. In a few other iterations, I turn these neurons off. I turn these neurons off. Okay. So instead of this connection going here and then going here, some of it directly goes to this neuron. This neuron sees the data from this point directly instead of through this.
So it makes this better?
This actually makes the neuron learn newer things, not just one thing.
Oh, okay. So but assuming beforehand that the the neurons that is turned off is the same as the neuron is on, right? Or it's not effective. That why you turn it off. Now, what
Well,
it yeah,
yeah,
what it
well,
means is like this with the neurons that with an X in it, like you cross it out. Is it like so? Is it like a bad one that you turn it off, or you
it's
just want to make it simple that you turn some random neurons off?
yeah. I'm not worried about it's good or bad. Even if it does best representation, it's okay. For this iteration, be quiet, sit it out.
So all of these neurons
So
are the same, and then we just randomly, and not randomly, but
correct.
we can just
It's randomly. It is
yeah.
actually random. You will randomly turn a few neurons off in every iteration.
Got it. So we turn some of them off so that we can train and to make the other neurons learn multiple things. That's the idea
Yes,
here, right?
that's the idea for exactly.
Thank you.
So the
But
yeah.
but before that, like the in the neuron in the brain example, you said that oh, if it learns two things at the same time, it's not efficient. Then then why do we make it learn multiple things and the result is simpler and better?
So we wanted to learn multiple things in the sense that we don't instead of saying we wanted to do multiple things, we don't want it to do the same thing. Okay,
Oh,
because that way it is not dynamic.
oh,
And we assume that being dynamic is what helps you learn patterns in its true form and not just memorize the data. If you do something repeatedly, you just memorize it and you do that one job fantastically,
so what
which
I
is the
understand.
hallmark of overfitting. Yeah.
Got it. So what I understand is that on the in the neuron brain example, it means that you don't want to one thing, no, one person, I mean, yeah, one neuron to do two job, because it's not efficient. And so how it related to this is that you want each neuron to focus on this, and then the other neurons that turn off now will be turned on later to learn something else.
Correct. Exactly. Exactly. Exactly.
Thank
So
you.
in a few iterations, I turn a few neurons off and I turn it on in the next iteration so that it starts seeing. Otherwise, there's no point in having it, right? So I randomly turn it off in this iteration. So I randomly turn, like again, that's a hyperparameter I can specify, and I'll say 10% of the neurons turn off. So if there are totally 50, there will be 5 neurons which will be off in at any point of time, but it won't be the same 5.
Thank you. And just for clarification, is that in during the hidden, not in a hidden layer, because you can't really control anything in a hidden layer, right?
Yeah.
This is
No,
happening in
no.
the beginning.
No. It is happening in the
Sorry.
hidden layer. It is
Oh.
because I can't see the output of the hidden layer, but I can just say that, okay, turn it off. Whatever you are doing, you don't do. That much control I can have over the hidden layer.
Okay, so because we get the output and we say that, oh, the error is very high. And so that's why we go backward and then turn off some neurons and see if the training's result gets better, right?
Yeah. So training result gets us. So this is completely not based on the back propagation or gradient descent or anything. Okay, we just randomly, instead of, think of it as we are, if there are 30 neurons at any point of time, there are 25 active neurons. That's all.
Okay, so we're just talking about training neurons now. Thank you.
Yes. Okay, Deepak.
So just a question on, when you're trying to like turn off certain neurons, are you reducing the layers in this, or the number of hidden layers stays the same? You're just turning off randomly neurons in each hidden layer. Like the random thing is not really random in the sense that all neurons in one layer is turned off.
No. So, internally, we don't know what's happening. We hope that it doesn't happen that way. But even if it happens that way, that's okay, right? Because the third hidden layer will now act like the second hidden layer. I mean, we are okay with that because it's only one iteration, right? Next iteration, again, it's going to turn on. So that's okay. So, but answering your first question, we are not playing around with the number of layers. We are only playing with the number of neurons. So it can be 2 in the first layer, 2 in the second, 1 in the third. Or it can be 1 here, 2 here, 2 there. So it's going to be distributed across the neural network. For what you said, for that to not happen, we should have a dropout number sensibly, right? If we say that there are 30 neurons totally in my neural network, and I'm going to turn off 10 of them, or 30, 15 of them, right? Very likely, at some point, every neuron in a layer is going to get turned off. Probably. Highly likely, right? And 50% dropout is not a bad number. People do 50% dropout. Okay? We are okay with that.
So just a follow-up there, like when you're doing this is all happening during the training, right? And when you're actually using the model like for testing, does it mean that you're still randomly turning off and doing those iterations, or everything is turned on at that point?
When I'm running the model, so when I'm running the model, it is only the model weights which are saved, right?
All the
So
neurons are turned on then, right?
all the neurons are active there. All the 30 neurons are active.
So the value of doing this in the iteration is like, what is the value of doing
The
this in the
the the value of doing this is the weights are not going to be very specific. The training is going to be a little more dynamic.
Mm-hmm.
It's going to learn from the data rather than memorizing the data. Once it has learned, those weights are frozen.
Got it. So the benefit of this exercise is that each neuron and it does get like it learns and ultimately like that benefits the overall
Correct.
neural net.
It benefits the overall network, overall model.
Got it. Got it. Okay. Thank you, sir.
Thank you. Another hand was up, but now I don't see it. What happened?
Yes, Professor. So I was just connecting this RMS prop earlier you mentioned. Is it that also with this the dropout? So whenever we train the model, we should have both of them. Then only we will get overfitting issue also solved and our training also efficient.
Yes. So that's what Niyaz was asking that time. That now we understand all the terms, right? He
Got
talked
it.
about optimization. He talked about regularization, and I
Regularization.
said that these are two different things. So optimization we solve using Adam. Regularization we address using this dropout and all that.
Okay. Got it. Thank you. Thank you.
So coming back to Niyaz, I think I hope this also answered your first question of working with two things simultaneously. Regularization, optimization, two different things, two different approaches.
Got it, Professor. Got it. Thanks.
Okay. Uh, so again, see, without dropout implementation, with dropout implementation, I think I have demos for all this. But can you interpret this? What is on the y-axis? Usually we saw a shape like this, right?
So here it should be accuracy because it's
So
going higher.
it is going higher, right? With each iteration, the number is increasing. So we are talking about accuracy, and you can see that as represented here. Metrics accuracy. Okay, that's the metric we are following. And if you see this during training, the network gained in 500 iterations, it got to around 95% accuracy, right? By 1,200 iteration, it got to 100% accuracy. It's extremely confident, overconfident, right? But when you present the test data, it can't go beyond 80, 79%. It can't go beyond 70 to 78, 78 percentage. This is a huge gap between the training and test. Okay. Whereas after implementing dropout, again, everything else is the same here. We are only introducing the dropout term. Dropout of zero point 0.4 means that 40% of the neurons I'm turning off between in every iteration. It need not be the same 40%. So 40% of 500, right? That's the number of neurons that is turned off in every iteration. Now, if you see this, it is much more jagged. The training is much more jagged, but it kind of, if I want to draw a line here on this, I would draw a line that would go something like this, right? So it never reaches 100%, probably 95, 96%, which is realistic. And the training accuracy is somewhere over here, okay, which is around 79. I mean, it is still a gap is there. I would want it to be narrower, but it is definitely better than the 178 um, uh, 78 situation that we saw in the previous without dropouts scenario, right? Okay. Another way to address this another general approach. Okay, this helps in multiple ways. The normalization that we are going to talk about, but mostly to help with the computation. So instead of sending raw values, we do some sort of a standardization or normalization, which is we do the z-scores, okay, or we reduce all the numbers from -1 to +1 or 0 to 1 kind of a thing with 0.5 as the midpoint and give some manageable numbers to the neural network. Okay. Now, what is the advantage of this? Let us say that I have a data set where one column, my x2, x3, then I have y. Okay, this column is all 0.5, 0.5, 0.6, 0.9, 0.1, 1, 0.85, and all this. Now I have another column which goes from, let us say, -1, um, 0 to 5. Okay, so this is 0 to 5. Or in the let's say it's a categorical column with three categories. 1, 2, 3. So 1, 3, 2, 2, 1, 3. Okay, it goes on. X3, let us say it has a bigger range. It goes from -10,000 to +10,000. Okay, so this is -10K. This is the next value is 5K, and then I have 0, and then I have 3K, and then 10K. Okay, I have all these numbers. Now, if I'm going to send all these numbers to neural network, computation really becomes an issue, right? Because the range of one of these is 0 to 1, the other one is 1 to 3, the other one is -10,000 to +10,000. So one of the approaches, one of the pre-processing that we do, which is specific to neural network, is to convert these numbers into standard z-scores. Okay, you remember doing z-scores in the first session, statistics, right? So convert that into z-scores so that we bring all the data, all the data points, all the columns around a common value, around a common zero kind of a value. Okay, with a zero mean. So that all the data is kind of together, and now the sensitivity to the weight changes and all becomes more standard, and the neural network, we are making the neural network's computational job a little bit easier. Okay, any questions? I'm expecting at least one question. Does this really work? Right? Is the first because it looks like these are computers. So, does it really make a difference? Surprisingly, it makes a lot of difference. Okay, when you give smaller numbers, the network is much more efficient in learning the representation of data. The problem still here is I do a normalization, okay, goes to the first hidden layer. Now, after the first hidden layer, what happens to the numbers? Again, all the numbers go all over the place, right? So you have to repeat the normalization after every layer if you want to maintain the normalization. Okay, so at every layer, at every hidden layer, the computation becomes easier for the neural net. We can one last thing, we can do a normalization with respect to the whole data, or you remember the mini batch which we sent into the neural network, right? We can do a mini batch normalization where the mean of that particular batch is taken rather than the mean of the whole data set. Okay. one of the things we can actually do is actually center all these values. Okay, center all these values around the mean of the data set. Mean of the data set. That's one way to do it. We can do a column-wise mean and then we can do a normalization. Or we can do just over the batch and we can do the normalization for that particular batch. All three things work, but mostly people do a batch normalization. Okay. Questions?
Yes. Thank you. I got this, but I think I missed the part about why does it go everywhere again after each
Ah,
layer?
okay. Um, because let us say I for the first layer I do all the z scores for the 10 columns that I have. Okay.
Mhm.
So all the z scores go through the first hidden layer. The first hidden layer does its own activation functions, right? It does ReLU, it does sigmoid, whatever it wants, it does. Now it's no more within the given range of minus 1.64 to plus 1.64 because it has done its own thing. It has done a square root, it has done a PCA, some cube root, or it has done a sine, cos, something it has done, right? That's the non-linearity which this layer is introducing to the data.
Mhm.
So it does its own stuff and it changes the numbers. It also changes the range of the numbers.
Yeah. Mm-hmm. So it changed the number. It changed. Sorry. I missed it again. So we already normalize it around the mean of the data
Yes,
set, and
we
then now we
renormalize
use the
it.
functions. Now we use the functions to play around with it. So why does it jump all over again?
Yeah,
Uh,
because it's not within that. The point of z scores is all the numbers are between minus 1.64 to plus 1.64. Okay. Let us say there's a neuron which does x squared. Whatever number it comes, it does square of that number. The square of 0 is 0, square of 1 is 1, square of 2 is 4, right? Now
uh-huh.
it's no more within minus 1.64 to plus 1.64 because already it
Because
has like
of
if
function,
huh?
because of all of the calculating and
Because of what
functions.
it does. Yeah, because of one of the things that it does.
And then you need to do normalization again for every single layer.
Again, yes.
Um, Sorry, I kind of get like 90% of the z-score, but if I put in one sentence simply, how does it help again? Like whenever we
Okay.
want normalization, we do z-score. In which situation do we use z-score again?
I mean, normalization is Z score, right? Z score is the same. You take the mean and you subtract it from the standard deviation. You bring it within some sort of an accepted values, range of accepted values, some manageable range, right? That is basically normalization. Yeah.
Yes, thank you. Thank you.
Thank you. Any questions still here? Just a
Professor,
quick yeah, go ahead.
yeah, you were showing the normalization, something like a z-score normalization.
Yeah.
Now it is between -1 and +1 kind of a thing. So now, if I have a quantity which is technically a 0 to 1 kind of a quantity, even that has to be brought to +1 -1 for a neural network.
You see, there is nothing called it has to be brought. It makes things easier for the neural network. We can
Hmm,
skip the whole normalization and the neural network will still train.
hmm, hmm.
Okay. But somehow normalization helps. That's all.
Got it. Thanks.
This is a small playground. You can actually open it. I'll give the link in the chat box, or you can just type TensorFlow Playground. TensorFlow Playground in Google, and you will be taken to this website, playground.tensorflow.org. Did it work? Did the link work? Okay, the second neural network playground. And this lets you freely adjust. Uh, in our lab, we'll be going one step beyond this actually. So ratio of training to test data 50. So we are doing a 50-50 split here, which I don't want to do. I want to do a 70-30 split. Batch size is 10. The noise is basically what happens is like how overfitting reduced dropout reduced the overfitting, right? So one of the other approaches that people do is they add deliberate noise into the data, right? So the idea is if I give too clean of a data, again it memorizes stuff. So you in any data you can actually induce a little bit of noise. So I'm just adding 15% noise, 20% noise. So I'm going to keep it zero for now to keep things simple. Okay. Again, so that is something that you can do. And I'm slowly building a neural network. Let's start with just one. Okay. One input layer. I'll start with no hidden layer. So at this point, it is only a perceptron, a single neuron, right? Because it draws only a straight line. If I click on this play button, the neural network starts training. Yeah, go ahead.
Yes. Sorry. For the noise, does it mean the dropout?
Mm,
Sorry. The
It's
definition
a
for the
different.
noise, Professor?
It's a different concept, but it does the same thing that dropout does. In the sense,
So
I mean,
what?
it leads us to the same place. Like it reduces overfitting, the same way that
Yeah.
dropout reduces overfitting. What is
And
noise
what
is
it means
basically,
is, yeah.
yeah, basically I'm trying to add noise to the data. If I have a clean row, I'm probably um, adding some missing values, increasing the range of some values, deleting a few values. That is noise. So my clean data set, I'm making it unclean
What?
with the assumption that
Okay.
not too
So,
much. That's why not too much. I'm adding a
yeah.
little bit of noise to my data set.
But what I mean is, so regarding the concept of dropouts, is that you
Hmm.
want to turn off something in order to make
Ah,
something better. And
correct.
noise, if I understand it the same way, it means that the more noise it is, maybe the more turn off you want,
In a way, yes, in a way.
right?
But we are not working with a neural network. We are working with a data set actually. Noise
Yeah, but
adds
it's
stuff to the data
similar.
set. It's similar, exactly.
But but what kind of stuff? Sorry, Professor.
What?
So we have a lot of data set now. So and now
Hmm.
it's clean. Why do we want to add like crazy stuff in?
We are assuming that if the data set is too clean, the neural network will overfit it.
Oh, so it's
So
like you
in
want
the
to
in
do
the
better in test. It might test,
yeah,
or
so it's
it
yeah,
might be like it might like mimic the real life situation.
hmm,
That's what it means,
correct.
right?
Correct, exactly. So if you take the analogy of test, you ask an ambiguous question, and you while training the person, instead of giving like a clear definition of question like define what is a neural network, you ask something really vague like what do you think network of neurons in a computational system will do. Right
Got
now,
it.
the question itself is ambiguous, but it will help you think and it will answer you. You will figure out that the question is actually the definition of neural network.
So it's the same thing, right? Like right now, doing with like the LLM thing. The better the LLM is, the more it will understand per people, regardless of how
Hmm.
that people explain. Maybe very simple. I mean, maybe very vague, but it can really
Yeah,
understand. Thank you.
probably. I think there's a similar thing in the chat. It says same purpose like prompting. Yeah. So so in prompting, how is it related? Like how to get the best out of the LLM, right?
Yeah.
Yeah.
So the good LLM is that even when you give vague prompting, it
Hmm.
still understand you perfectly.
Correct.
So
Yeah.
you want to
So
introduce some person.
very similar concept
Thank
in the chat box also. Yeah.
thank you.
Thank you. Okay. So now this obviously it cannot build anything useful here because it's only a single neuron. Now let me add more input features. Okay, and see what happens. Right? Still nothing's happening. I am adding more and more input features and I'm seeing what's happening. Okay. What's this? Okay. So again with three input neurons, nothing is happening. So I'm going to have one more. Okay. And now suddenly something makes sense here.
And on the right, that is somehow it's on the models, right? When
Yeah,
in
so
real
this is the model,
they
yeah.
talk about models, yeah. When they talk, they mention models, and that's what it means. Like it can be
Yes.
like hundreds of different models,
Mm.
and it can be resulted in like the picture like that. Thank you.
Yes. Well, okay. So again, only this is not explaining it. I'm adding more. Okay. Now I'm doing something different. And let me, instead of just changing the input features, I'm going to add more hidden layers. Okay. And I'm going to see what's going to come out of this. I added one hidden layer with one neuron. Let us see if this works. Did the network converge? It kind of converged, right? But still nothing is happening. So I'm adding one more neuron in the hidden layer and I'm repeating it. Now, if you see this, there is a vertical line and horizontal line. And this neuron is basically combining these two lines into some sort of a slanted line, right? And this is creating another slanted line, but in a different angle, at a different angle, right? What we need is a circle. So none of it is able to get there. Let's try to add, sorry, let's try to add one more neuron and see what happens. So now we are combining three. So now we have basically combined three lines. Uh, one line which goes like this, another line which goes like this, another line which goes like this. So together it has created this inverted triangle like thing, which is actually decent, right? Different combinations of the two of just one vertical line and one horizontal one. I'm going to add one more neuron and see what's going to happen. Now I'm getting a nice square like thing. So this is the first vector, first line. This is a second line at a slightly different angle. This is a third line and a fourth line. Now this is, if you remember, this is very similar to what I showed in the first class, where there was this data and I had these different lines, and I said that a circle is basically lines in different angles. Yeah, well.
Yeah. Sorry, I just want to clarify. The first is the activation. What does the TANH mean?
Oh, that's a tanh activation function. So I can change it to
So
sigmoid.
the sigmoid and then 10. And we
Yeah,
haven't
the
learned that
tanh.
already. Yeah.
I think I showed it in one of the sessions. I think in the
Oh,
yesterday's session.
never mind. So it's
Yeah.
the activation functions that we choose. And then
Yes.
regularization. Could we
So
click on
L1
that?
or L2 regular, L1 or L2 regularization.
It means
Then we can
layer
choose.
1 and layer 2.
No, so we'll talk about it when we do CNNs. But I think this should have been done at some point in the past. Regularization should have been.
Yeah, it was taught by Dr. Rajan, the
Yeah.
L1 and the L2 regularization. So in the fundamentals of machine learning, it was taught well.
Okay.
Never mind, we'll come to that. Okay. So I'm
And
worrying too much about that. Let's concentrate on these two alone for now: the learning rate and the activation, because that's what we have learned till now. So I'm going to deliberately increase the learning rate to a big number and see what happens.
oh,
You see how the neural network changed here, right? If I make it to an even bigger number, what I should. You see how increasing the learning rate just flip the whole thing. Now it's not doing, it's incapable of doing because it is just bouncing off the feature space. Because the learning rate is too high. It is missing the minima.
may I clarify
Here we
on the
have a
color?
very small learning rate now.
So the orange color is the
At this
neuron?
point, yeah. Yeah, so at this point, the colors are, I would say, not of much use actually. So the orange color basically represents the orange points. The blue represents the blue points. I mean, the features related to the blue points.
So they're just features. And
Yeah.
yeah. And then on the first hidden layer, so that like the shape in there, sorry, in the square, like the shading, it means the weight, right? You put
So
into the
yeah, so at this point, it doesn't really have any sense because we have not trained it yet. But this basically says that this neuron is capable of drawing a single vertical line. This neuron is capable of drawing a single horizontal line. That's what this means. Okay.
Yeah. So it understands lines.
So
That's what it means.
yeah, so this neuron, which is getting input from this and this, will combine this vertical line and a horizontal line into some sort of an angled line. And you can see that now. right? So you see how this has combined these two into some sort of a line here.
Okay.
Okay. So I'm going to change the learning rate to something really, really small and see how that works. You see, concentrate on this part of the neural network.
Uh-huh. And the batch
So you see how
size is
slowly it
limited
trains.
to 100. Sorry, Professor.
10. Batch size is
Yeah.
10 here.
And the maximum is 30. 30 out of 100, right?
Probably I've not tried that.
Yeah, so it's just a random
Okay.
number.
But
Thank you.
yeah. But you see, if I have a very small learning rate, the neural networks trains, but it trains really, really slow. You see the shape of this. If I have a very big number, how it is suddenly all over the place, right? And by changing to some other number, I'll start with a small number, let the network train for some time. This is the number of epochs. So it's 170 epochs running now. Now let me increase the learning rates. You see how the decay, the shape of the decay function that we saw, we are able to replicate that here, right? 0.03. I will now again, I will change it to some other number. Right? So that is the learning rate decay. Now I did this manually. If you set the decay to a particular value, it does it automatically. Okay? I think we can continue with this in the next session. Meanwhile, you can also play around with this. Very nice, lot of other data sets are there. If you don't get time, that's okay. We can start the next session with this little visual exercise of what we learned. Any questions? Okay. Thank you then. Thank you for the wonderful session. Let's meet the next Saturday. Have a happy weekend. Thank you.
Thank you.
Thank you.
Thank you very
Thank
much.
you.
Bye
Good
bye.
night.
Thank you. Bye.
Thank
Thank
you.
you, Professor.
Good night.
Good night.
Bye.
Thank you.